Swayam Prabha. Digital India. Educated India.
Now, yet another interesting input. We will see later why it is interesting. A sinusoid. Okay. And actually, I could have a arbitrary phase shift here. So, Vp cos omega t plus phi. Okay. Then again, I find Vc, but of course, I could find any other variable in the circuit also, right? I'll always use this very simple circuit as an example because I don't want the algebra to overwhelm what I'm trying to convey here. But this procedure can be used for other things also. Similarly, for that exponential, right? And for a first order circuit, as long as you know that, let's say we had exponential st as excitation and the actual circuit was very complicated, you still know that the steady state response is exponential st times something, and then the natural response or the transient response is exponential minus t by the time constant of the circuit, and by manipulating the constants with initial conditions and so on, you will be able to get the answer. Okay. So, now in this case, what do you think is the solution to this? Again, I want Vc of t, right? Vc of t, it will possibly have multiple parts. What do you think it will consist of? First of all, it will have the natural response, okay, and then force response. What is the force response going to be? It can be anything, because I mean, if you differentiate cos, you get sine, and if you differentiate sine, you get cos. Okay. If you think of this as sort of balancing act, where if you have cos omega t plus phi on this side, you should have it on that side so that it cancels. Okay. But then Vc cannot be just cos omega t plus phi, because when you differentiate it, you get sine. So you expect that the general form of it there are many ways of writing this. I could put some other angle theta there and then try to cancel it also. Okay. Alpha cos omega t plus phi plus beta sine omega t plus phi. I will write it in this form. So clearly, if I differentiate this, I will get okay. So now you can put this in there, put this in there, and you have two constants, right? Alpha and beta. So you have to balance the sine and you have to balance the cosine. So from that you can get these two constants. Okay, you can never balance a sine with a cosine, right? That's not possible. So you have to take the cos terms out and the sine terms out, and then you can get the stuff. Of course, this will give you only the forced response. The general stuff will have also the natural response. Okay.
Please derive the complete response including the natural response. I will have a separate lesson in which I will show the derivation. You can compare your answers to mine.
So this is one way of doing it. Can you think of any other way of doing it? I mean, knowing what we know so far. Another thing you can do is this Vp cos omega t plus phi is Vp by 2 exponential j omega t plus phi. I mean, the whole thing is multiplying this. Okay. So we already know the solution to exponential st. Okay. So this is nothing but, again, I have another phi here. What do I do? This is exponential j phi exponential j omega t. Okay. So that's just another multiplying factor. So I know the solution to Vp exponential st. Okay. So all I have to do is substitute s with this j omega, and then that Vp with this Vp by 2 times exponential j phi. Okay. The constants I have to adjust, isn't it? That's all. There is some other constant here. So I do it for this one and I do it for that one, and I can add up the results to get the forced response.
Please derive the complete response including the natural response. I will have a separate lesson in which I will show the derivation. You can compare your answers to mine.
Is this okay? So there are two ways of doing this. First, you know that if you have a sinusoid, the solution is always some linear combination of sine and cos. Okay, alpha cos plus beta sine. You can always take it as the solution, and then you plug it into the differential equation and find the constants. You will get two equations, one from balancing the sine and other from balancing the cosine. Okay. Alternatively, you can express the sinusoid as combination of complex exponentials. A very useful concept. Actually, there is no life as electrical engineer without complex exponentials or without complex algebra. Okay, we will move to that. So you now have exponentials. That is easier. Okay, you know that the steady state response to an exponential is only that exponential. Okay, with some scaling. So you do it for exponential plus j omega t, exponential minus j omega t, and then add up the results. Okay. By the way, one thing I didn't emphasize earlier is that we always have the steady state response and the natural response, and we know that linear circuits obey superposition, but in this case we have to be a little careful. The steady state response follows superposition by itself. That is, if you have an input x, you find the steady state response, input y, some other steady state response. The steady state responses will superpose. Okay, if you have alpha x plus beta y, this will be alpha times the first solution plus beta times the second solution. Okay. The natural response also scales with the initial condition. Okay. But what you cannot do is, for some initial condition, you apply one input, find the total response. With the other input alone, find the total response. If you add up, you will get the wrong result. Okay. So the steady state response itself follows superposition, and the natural response itself by itself scales with the initial condition. Okay. So you try it out and see. So let's say this steps to 5 volts at t equal to 0, and then this also is a 2 milliamp step at the same time at t equal to 0. Okay. Okay, so maybe you take this to be 1 kilo ohm and 1 nanofarad. The particular things don't matter. So now, first you find the total response taking everything together by taking the Thevenin equivalent, etc. Then you try to do the superposition. Take the total response with this 5 volt source alone, total response with this 2 milliamp source alone, and then add the two and see if you get the same result as the actual total response or not. Or if not, what exactly is wrong with it. Okay. So the exercise is to
try superposing the total response from the two sources when you have some given initial condition on the capacitor.
Okay, and you assume that you have some Vc of 0 on the capacitor. Okay.